All right, welcome everyone. Today we are very happy to have David Dunsky from NYU to give us a seminar on primordial black holes from axion walls. Take it away.
Thank you very much for having me. I'm very excited to be here. As just said, I'm going to tell you a little bit about ways to form primordial black holes in axion models, excuse me. And this is some relatively recent work done with Marius Consor at NYU. Now, before getting into the details, I want to just go over briefly just a motivation and kind of the key idea of the talk, right? And so first thing is axions. Why do we even want to study them? I'd say there's probably two main reasons why axion models are very interesting. The first one is that axions, or the QCD axion, can be a solution to the strong CP problem, which is the surprising absence of the neutron electric dipole moment. Another very interesting reason why axions are very well motivated is that they're very easily to be produced cosmologically, whether from misalignment or from strings and domain walls, so that axions, whether talk about the QCD axion or ALPS, axion-like particles, that they can be a natural dark matter candidate. And people in the lab will currently probing these axion dark matter as a function of this axion decay constant, which roughly tells you how strong or weakly coupled these axions are to standard model observables. Now, the same axion decay constant is also very intimately tied to cosmology. And something very interesting happens when the universe reached a temperature that was at least the scale Fa, this axion decay constant. So kind of in the standard cosmological lore, when the universe cooled below this axion decay constant scale Fa, then axion strings formed, which are large concentrations of energy density, such that when you go around these strings in physical space, the axion field A over Fa changes from 0 to 2 pi. Now, regardless of how many strings you form to begin with, roughly these strings will reach an attractor solution over time as the universe expands and the temperature cools, and you'll reach this attractor solution known as scaling, where roughly these axion strings are such that their typical radius of curvature and their typical separation between strings is the same order of magnitude, same scale, which is set by the horizon. So these axion strings will dynamically evolve to reach this attractor solution until something interesting happens when you get closer to the QCD phase transition. Now, near the QCD phase transition, every axion string becomes attached to a domain wall, which I'll explain in much more detail soon. And these domain walls you can think about are like surfaces of large concentrations of axion energy density. Now, if there is no inflation that happened before while these strings formed, as Li and Tao and Casey have discussed before, if their strings are in the horizon at this time, you get these walls attached to these strings, and very shortly after the QCD phase transition or near there, these axion walls, domain walls, will pull on the strings exactly like that. If you want to see more detailed information, look at some more serious simulations of various groups, such as Giovanni and Ben Softy and so on. But the key thing is that these axion domain walls will pull on the string network near the QCD phase transition, and the whole network will decay, and lots of axions will be emitted, such that today there is a large amount of axions, which they can be the dark matter. And that's kind of the standard cosmological picture. Now, what I want to say, the key point of this talk is that while every axion string becomes attached to the domain wall, it's possible, though rare, to form axion domain walls, these surfaces that are not attached to any strings, but are enclosed surfaces. And what's cool is that one can show it's energetically favorable for these surfaces of large concentrations of axion density to shrink. And as they shrink in size, like energy is conserved, so they become more and more relativistic. And they can shrink to a very small size, and potentially you can compress enough energy into a Schwarzschild radius and form a black hole, so that today there is both axion dark matter from the previous axion strings and so on that were under misalignment produced previously, as well as some small amount of PBHs. And so the goal, or what I want to talk about, is actually how we can estimate these abundances for QCD axions, for ALPS, and so on, and see what fraction of PBHs we can get. So kind of the outline of this talk, we'll talk about First, the cosmology and the formation of the topological defects, both strings and domain walls. So we'll go over those. Then we'll talk about how these walls behave dynamically after they're formed. And then finally, now I will talk about the dynamics of them during their collapse and see exactly their efficiency of PPH formation and their relic abundance. Okay, so first we'll talk about these axion topological defects. So you can basically understand the topological defects in a given model by looking at the given symmetries that are respected at given points in time. So for the axion at very high temperatures, it's described by a complex scalar field phi. And this Lagrangian respects some U1 symmetry. So if I take this phi field and I multiply it by a phase, this Lagrangian is invariant. And this potential, this VPQ, is just shown as a fiducial example, some U1 symmetric potential, this wine bottle or Mexican hat potential shown here. Now, something special happens as the universe cools below the scale FA, in that this phi field develops a vacuum expectation value. So it starts off at unbroken at this minimum over here, or excuse me, at phi equals 0. As the universe cools, this potential becomes somewhat like this wine bottle potential, and this phi field will fall towards some of its minima, which you can see are along the rim of this potential. And this vacuum expectation value is such that the magnitude is Fa, that's the axion decay constant. And the axion that we know and love is just the angular degree of freedom of this axion, of this complex scalar field. So the axion parametrizes basically which minima you are along this rim, right, in the complex space. Okay. So how does this manifest itself in the universe? So what we can do is basically do this is the Kibble mechanism effectively, and this idea is tied to this idea from Sakivi as well. And the idea is, let's look at this wine bottle potential. Let's kind of look on it face down, bird's eye view, right? So we know that the symmetry breaking of this complex scalar field, the universe wants to go into one of these ground states, and there's many of them. There's a continuous amount of ground states. It can fall anywhere along this rim, excuse me, of this hat. Okay, so imagine I take my universe and let's look at it just a cross-sectional slice of my universe, which is shown by kind of this grid over here. And each grid point or each square is going to represent basically a different correlated patch of the universe. So at minimum, you can think at least this is the size of the horizon. So different horizons will actually have different causally connected patches, but in principle, it could be a much smaller size. But this is just, each square represents the correlation of my complex scalar field at the time of my symmetry breaking. Okay, so different parts of my universe, different squares are gonna, by chance, randomly fall along into one of these ground states, okay? So when I put an example of a theta 1 here, what I mean is that just by chance, this patch of the universe happened to fall into the ground state that was somewhere between, say, 0 and I guess 2 pi over 3. Theta 2 happened to be, theta 2 means that the universe happens to fall into a ground state somewhere along this part of the ground of the rim, and theta 3 in the red region. And so in my universe, this cross-sectional slice, I'm just going to randomly put different values of theta because it's just by chance this axion field, this complex scalar field will fall into one of these along this rim into one of these random new ground states. Okay, so that should show in here. Now something special happens in some parts of the universe. In particular, I can get some regions of space just by chance that are such that I have a region of theta 1, theta 2, and theta 3 in this kind of counterclockwise orientation. And that is such that in physical, this is in physical space, but it maps such that in this abstract field space, my minima go along theta 1, theta 2, and theta 3. So as I go in physical space, I go around this curve in physical space. I go in field space around the bottom of this potential, the ground state of my potential. Okay, and what's interesting is that if I look at different slices of my universe, this is just one slice I could do in 3 space, right? In 3D, I have to go look at many different slices. Is that if my thumb kind of points along like my right-hand rule, I wind around this point in physical space, which corresponds to a winding in field space, that my thumb can actually never disappear. It either will have to wind back and go back on itself, that is, its configuration of points are such that I can't just disappear, my thumb can never just go away, or it goes off to infinity, okay? And my thumb represents actually a winding number, or it's gonna be a cosmic string. And the reason why it's a string is that, well, for one, I just said like my thumb, which points along this direction of winding, is going to, it either forms a loop or goes infinitely in extent. But what it is why it's a string, it's a high concentration of energy density, because one can show that the solution of solving these Euler-Lagrange equations of motion for this axion field is such that a region of space where in physical space, I wind around this potential in field space. It is such that as I go closer and closer to the shared vertex where my thumb is located, my phi field gets closer and closer and actually is at this unbroken phi equals 0 part of my potential. And remember, at that part of the potential, right, the top of this potential well, I have a large amount of energy density. That's where my potential is maximized. So my thumb, which represented this cosmic string, is a concentration of a large amount of energy density. Okay, so for these cosmic strings, which formed at scale temperature of order Fa, when I break this U1 symmetry, I get these axion strings, which are the locus of points in physical space where my phi field remains unbroken, and I have a large amount of concentration of energy density there, because that's where that potential is maximized. Okay, one last point for these cosmic strings that we'll need a little bit later is that these defects in general are often described by kind of a macroscopic quantity, which is known as their tension. So for strings, we can talk about a mass per unit length, the string tension mu. It's very simple to parametrically estimate what the string tension is. It's going to be the energy density where the string is located, that is my potential where phi equals is unbroken, times my typical size of my string core. How large in physical extent is this large concentration of energy density? And it's just going to be set by the effective inverse mass of my heavy phi field, which is going to be of order 1 over Fa. So parametrically, my energy density times my cross-sectional area is of order Fa to the 4th times Fa 1 over Fa squared, which is of order Fa squared at the end of the day. Now, for global strings, which the axion is, you actually get a special correction to this. Because you have to technically integrate over an actual over all space, not just multiplying by cross-sectional slice, and you get this extra log factor, which is special to global strings. Okay, so that mildly improves or increases the string tension. Now, this occurs, these strings formed, as I said, near the PQ phase transition, and my thumb, which would randomly wind around in space, mimics this infinite string network shown here, and it's very wiggly, with typically eventually roughly one string or one typical curvature of the string per horizon, shown by this red circle. Now, what happens is that the string curvature that's inside this horizon is free to move and wiggle around, whereas curvature or scales that are much larger than this horizon are stuck. Causality cannot move them, right? Because my universe is not old enough for them to move an appreciable distance. So inside this little horizon, this curvature will move and wiggle around, and they'll intersect, emit gravitational waves, axions, and so on. And that little curvature will be reduced with time. And so as I progress in time, my universe, my horizon expands, and the strings within there can move and wiggle around, and they'll damp curvature on scales that are smaller than the horizon. So that over time, I'll maintain this sort of picture of roughly one string per horizon. So qualitatively, that's actually what the scaling behavior is, and why asymptotically we get this attractor solution of roughly one string per horizon, which mimics this typical size, how large my axion field is correlated at a given point in time. Okay. Now, what about these domain walls? Lots of strings. Well, let's look at the potential the axion develops near the QCD phase transition, which is shown here. So near the QCD phase transition, strong dynamics generate this cosine potential for the axion field, just shown as a fiducial example over here. I'm plotting 1 minus cos A over Fa versus the axion field A over Fa, which I'm calling theta here. So you can see what happens is that the axion develops a minima every 0 and 2 pi values, okay? So remember, the axion wants to go to its ground state eventually, right? Just as we were looking before at this Mexican half potential, this phi field wanted to go to the ground state eventually at the symmetry breaking. So the axion field near the QC phase transition, parts that are less than pi will want to roll down towards 0, and parts that are greater than pi will want to roll down to 2 pi, which are, of course, exactly the same minima technically. Now, how does this field configuration look like in real space? That is, if I want to look at my axion field, what does the field look like interpolating between these two possible minima? And what you can show by solving these Euler-Lagrange equations of motion is that your field, the axion field, will look something like this. That if distances are shown on the x-axis, the y-axis is my axion field theta, A over FA, is that at large distances on one axis, I go towards my theta equals 0 minimum. And on large scales, the other direction, I go closer to 2 pi. And you'll notice, so these are the true ground states of my universe, but you'll notice that I get a sudden increase in my energy density near this point, okay, that interpolates between 2 pi and 0, i.e. near theta equals pi. And what's happening there is if you look at this potential, right, my minima when A over FA theta is 0 and 2 pi, but I have a maximum, I have a lot of energy density at A over FA equals pi. So the key thing is that whenever I have in my universe regions of space where theta, A over FA, is pi, I've got a large amount of energy density there. That is the domain wall. So the points in space where my axion field A over FA theta is pi are surfaces of large concentrations of energy density, and those are my axion domain walls. Now, as I said, for these axion strings, as I wind around them in physical space, right, and my axion field is varying by 0 to 2 pi FA. So that means I have to cross a surface of theta equals pi for a given string. That means is that every string must cross theta equals pi as I wind around it. That is, every string must have an axion domain wall attached to it. There's a large amount of energy density, a surface of it, emanating from every string, kind of like a shark fin, a fin emanating from like a shark, for example. Okay, now there's one more quantity that we want to calculate that we're going to use again and again, and that is the tension of these domain walls. This is kind of this macroscopic quantity. Okay, and we can estimate parametrically what it is. It's just going to be the energy density where my domain wall is located, which is where surfaces of theta equals pi, times a typical cross-sectional slice of the thickness of my axion wall. Okay, well, what parametrically is this energy density at theta equals pi? You can see it's going to be of order ma squared fa squared. And the thickness delta is going to be of order the inverse curvature of this potential, which is going to be just my axion mass, or 1 over my axion mass. So parametrically, you expect this tension, this mass per area of the wall, is going to be something of order ma fa squared, and indeed a more careful calculation shows that that coefficient is of order 8. So the key thing to remember is that the larger my axion decay constant is, the greater mass per area of my domain wall is, which means that for larger FA, I'm going to get domain walls of very large mass, which is going to help them actually form PBHs if they can collapse. Okay. Likewise, since I'm talking about a mass per area, the larger the area of this domain wall, the greater the mass will be. Okay, so that will be, we'll keep that in mind. Now, what I just showed you is that every axion string becomes attached to a domain wall because the domain walls are going to be surfaces of constant theta equals pi, and every axion string has to wind around or has to cross the surface of theta equals pi. Okay, but David, where are the enclosed walls that you mentioned where I'm not attached to any string? Okay. Well, let's see how we can estimate that abundance and how they form. It's going to be very similar to what we did before. So let's look again at the circle of minima for the axion field. The axion can go from 0 to 2 pi. That's the brim of this potential for the complex phi field. Okay, and as I said before, for my axion field at theta equals pi, I have a domain wall that emanates from it. So here is an example of like an axion string going into the board. Okay, so at surface of theta equals pi, I've got a large concentration of energy density. That's my domain wall. And as before, I'm going to take my universe and I'm going to look at a cross-sectional slice of it. Okay, and what I'm going to do is, I'm going to look at my circle of minima, and by chance, I'm going to just put random values of my potential axion field, which can be anywhere from 0 to 2 pi. So here again is a cross-sectional slice. What I mean is that in this region of my universe, theta 2, here I put a theta 2, which signifies that the axion field near the QCD phase transition is somewhere between pi over 3 and 5 pi over 3. Theta 1 means that just by chance, random chance, that the axion field is somewhere between pi and pi over 3, etc. Okay? So the actual physical size of these squares, you want to think about them, are the correlation size of my axion field near the QCD phase transition which is just set by my strings, my string separation and my string size. Because my axion strings, which are in scaling, tell me how correlated my axion fields are in space. So the typical distance between my strings is the given correlation size of my axion field. So to identify these actual squares roughly with a physical distance, right? This is just geometry here. To identify these with physical distances, I can think about these as roughly the string separation over a horizon. So roughly speaking, each square represents a given horizon of patch of my universe, which can have some random value of the axion field between 0 and 2 pi. Okay, now let's identify where all the strings are located. So again, the strings are going to be the regions of space where in physical spaces I go, I wind in a circle in physical space. I trace the bottom of this potential well from 0 to 2 pi. So in this region, for example here, I go from theta 1 to theta 2 to theta 3 back to theta 1 by chance. So I wind around a string that goes out of the board towards us here. And this white dot here, I've got the opposite configuration. In physical space, I'm winding in the opposite direction. You can think about it as a string puncturing the board, going into the board here. Okay, so roughly you expect, and what you see is you get by chance, roughly one string per horizon or so. Okay, so again, I'm just putting random values of the axion theta field here, which corresponds to the potential minima of the axion right before the QC phase transition. Okay, now what about the domain walls? Well, if we go back here, we can see that whenever I have a region of theta 1 adjacent to a region of theta 3, because the axion field is continuous, I must cross a region of theta equals pi. So what you can see is that in red here, I've got theta 1, theta 3, theta 1, theta 3, theta 1, theta 3. So I must have a domain wall that is crossing this region here. So this is like a cross-sectional slice of my universe, cross-sectional slice of my domain wall. And as promised, you can see that every string has to be attached to the domain wall, right? Because every string is defined by going around 0 to 2 pi in field space. Okay, that means I have to cross the surface of theta equals pi. I have to have a domain wall that emanates or is attached to every string. Okay. But what you'll notice is, by chance, I can have a region of my universe where I have just theta 1 surrounded entirely by theta 3. Okay. So in this case, I have an enclosed wall that is not winding around any string. And you can see this is just a geometric basic, just a geometric probability, okay? It's what are the chances that I have a region of theta 1 surrounded entirely by theta 3 without winding around going back to theta 1, theta 2, and theta 3, i.e. a string, okay? And what you can do is, this is just a two-dimensional slice, but you can imagine doing this in 3 space, just randomly assigning to each volume of each lattice site, which represents roughly a horizon volume. I can assign random theta 1, theta 2, theta 3, and that will tell me that regions that are adjacent between theta 1 and theta 3, I have a domain wall surface that separates the two regions. And so you can imagine doing this in 3 space and looking at how many of these enclosed walls I get and how big they are, and what is their probability of finding them as a function of how rare they are. And indeed, we can do something like this. So what we did is, first, we took a 3D lattice and just randomly assigned these values of theta 1, theta 2, theta 3 to determine where we have surfaces of domain walls and see where we get enclosed domain walls, just how rare they are. And what you'll find is that roughly you'll get 1 per 1,000 of these correlation volumes, each of these grid points, you'll find one of these very rare enclosed surfaces, these enclosed domain walls. So first of all, this is somewhat rare, 1 per 1,000 horizons near the QCD phase transition, of course. And this is part of the reason why people in some simulations have not found these, because most of these very intense simulations only can simulate a couple of horizons. So the chance of finding an large enclosed wall within 1,000 horizons is fairly rare. But here what we can do is we can statistically get information about how rare these enclosed walls are. Not only that, is that because it's just a random process, you can see it's a probability of happening. You can see that there's some regions of space where I can have even a larger number of grid points that are surrounded entirely by a domain wall. It's just rare to happen, but we can count them up too. And here I just show the number of simulations we do, where we just take I think it was a 50 by 50 by 50 cubic box size and randomly assign theta 1, theta 2, theta 3 to find how to count the number of enclosed walls. So we get roughly 1 per 1,000 of these per horizons, you'll get an enclosed wall of 1 grid point of 1 cubic lattice. Roughly 1 every 10 to the minus 5 horizons, you'll find one of these enclosed walls that's even bigger, that spans 2 horizon volumes, and so on 3 and 4, and they're just rare. In fact, what this is actually known as percolation theory. And there are some estimates or some ansatz for how you expect in percolation theory, these cluster sizes is what they're called, to be distributed as a function of size. And indeed, one of these ansatz is that you should expect them to be exponentially distributed in size, is that they should be, the size of these enclosed walls should span something as e to the minus volume of these walls to the 2/3 power, okay? And at the moment, we can only simulate up to roughly 4 of these enclosed wall sizes, and they do indeed follow this equation fairly well. That is roughly the smallest ones of 1 per 1 horizon volume enclosed wall are roughly 1 per 1,000 horizons, and then the bigger walls are rare and rare following this exponential e to the minus v to the 2/3 formula. Okay. So one thing I will want to say before talking about a kind of a continuous version of this to corroborate and get more statistics is that the larger the wall is, the better the chance of them forming a PVH is. Because the larger the wall is, the more mass I have, which means, or the more area I have, the more mass I have, which makes it easier to form a black hole because the bigger the mass, the larger the Schwarzschild radius. Moreover, these walls, since they're just formed by total random chance of my correlated axion domains, they can be bigger than my horizon. And because they can be bigger than the horizon, they can actually expand briefly with the expansion of the universe, and they can grow and you get more mass out of them. So I will talk about that shortly, but I want to first say, what I just showed you was a method due to Sakivi is kind of a discrete method of taking a lattice and randomly assigning values of the axion field to see where I have surfaces of constant theta equals pi. Now this is basically a coarse-grained snapshot of the universe near the QCD phase transition, but the axion field is of course not discrete. It is continuous. And what we'd like to do is basically extend this or generalize this to a continuous version of this algorithm, this basically this Kibble mechanism from a Sakivi algorithm. So what I just showed you is basically saying that I have given an axion field, I'm saying that it's entirely correlated within a region of order the horizon size, and it's entirely uncorrelated in a region outside my horizon. So that's why I just put by random chance, I assigned a different value of the axion field to that lattice site. Okay. Now, what we can do is we can generate a continuous random field with these this type of correlation function, or one that is actually a correlation function very similar, that is a field. We know the axion field is very correlated within regions of order the string separation, that is the horizon size, or roughly L, and is very uncorrelated, it's very random on distances on scales much greater than that. So we want to generate a continuous random field to find exactly where we can get surfaces of constant theta equals pi and identify our domain walls. Now, in principle, we could take that correlated function I just showed you, this box function, and generate a continuous random field with that. However, numerically, it's actually a little bit tricky to generate a continuous random field with a box function like shown. So what we did instead is we're taking a similar correlated function, should be correlation length, that's exponentially distributed. That is, my axion field is extremely correlated on distances in parts of my universe that are much smaller than my string separation scale L, and my axion field is very uncorrelated on distance scales much greater than my string separation scale L. Okay, and we can generate a continuous random field like so. And we can look at surfaces of constant theta equals pi, where I know I have my axion domain wall is located. And what you find is that you get a very kind of coral reef-like structure. And what I'm showing here is this is kind of a patch of my universe that's 20 by 20 by 20 units of this L wide. You can think about this L, we can identify it with a physical scale by identifying it with this basically the string separation or the horizon size, T. So this is roughly 8,000 cubic volumes, horizons of my universe near the QCD phase transition. Thank you. All right. So what you'll see is that this purple region here, which is my surface of constant theta equals pi, i.e. this is my infinite domain wall network, is that my domain wall network is very Brownian, very random on distance scales much greater than my horizon size L, right? That's just because my field is entirely uncorrelated on separations much smaller, much greater than that. Now, this is a domain wall network that you find, and it looks like it's just one big infinite wall network, and indeed, most of it is. However, you can kind of shave off this coral reef-like pattern, and you can look inside of it. And if you do that, what you'll find in this particular case, this random run of generating a continuous random field with a given correlation length shown here, is that you'll find by chance, again, these, in this case, two surfaces, enclosed surfaces of constant theta equals pi that are not part of this infinite wall string network shown here in this purple. And beautifully, if you were to count these up and you just do random Monte Carlo statistics where I generate these random fields and count how many of these enclosed walls I get as a function of horizon volumes, you'll find exactly basically the same result we found before for the discrete case. You get roughly one enclosed wall per 1,000 correlation volumes, L cubed or horizons. Not only that, but you can get more information too. You can confirm as well how these walls are distributed in size. So as I said before, you expect many of these smaller walls to be of order the horizon size. That's the typical that's the typical correlation length of my axion field. But by chance, I can get random adjacent regions of space to align such that I have an enclosed wall that's even bigger than the horizon. And what you'll find is something from using the continuous random field generation, the number of enclosed walls versus their typical size in units of this arbitrary scale L, which again, you can identify as of order the horizon size T, is that you'll find these guys are logarithmically distributed in number density number density is e to the minus r squared, which is exactly what you expect from the discrete case that goes as volume to the minus 2/3 power. So this is a nice another expectation from percolation theory that that agrees with the discrete case was shown previously. So again, you get roughly 1 per 1,000 horizons of order correlation length size of order of the horizon, but you can get a distribution of enclosed walls that are much bigger than the horizon, though they decrease in size or decrease in number density. Not only that, but you can also get information about how these these enclosed walls look like geometrically. That is, these enclosed walls are of course not perfectly cubic as we would expect from a discrete model. And they're not perfectly spherical, as some might expect. And this is important because a perfectly spherical wall, as we'll discuss shortly, can collapse much more easily to a smaller point than a wall that is not perfectly spherical. And that will hinder PVH formation. So we can gather statistics about the shape distribution of these enclosed walls. And what you find is that they typically will have some ellipticity, some semi-major to semi-minor axis ratio that is about roughly 1.4 times longer on the longest side, the semi-major axis, compared to their mean axis ratio. And their smallest axis will typically be about 0.6 times their mean axis size. The key thing to note for this is that most of these walls are not perfectly spherical, and this will hinder PVH formation and something we need to take into account when estimating the abundance of these enclosed walls. Okay. So just to recap, what I just showed you was a way to estimate the number density of enclosed walls and their size distribution. Roughly, you get one enclosed wall per 1,000 horizons with the size of order of the horizon, and a smaller number of walls that are super horizon. Now, what happens dynamically to these enclosed walls once they form? Okay, well, let's look at a wall that initially has some radius at formation R0, which is some fraction alpha of the horizon, so shown here in red. Okay, now because this wall is super horizon, we'll actually get stretched with the expansion of the universe. So this wall will expand with the scale factor as A of t compared to the scale factor at formation. Now this scale factor will generally scale as time to the 1/2 or time to the 2/3, depending on whether you're in a radiation or matter dominated era. However, the horizon scales as time as t, so that means is eventually the horizon will catch up to the wall because the wall scales with a smaller power of time. And so eventually the horizon will catch up to the wall And the wall has grown in that time. And if you just compare when my radius matches my horizon, what you'll find is that my radius of the wall, which has grown, is now a factor of alpha times its initial size in a radiation-dominated era, or alpha squared times its initial size in a matter-dominated era. And the reason why it's bigger in a matter-dominated era is because my scale factor grows faster with time compared to a radiation-dominated era, and hence the wall can expand further before the horizon will catch up to it. And so you get free mass from this. And so what this means is that the larger my alpha is to begin with, which is set by the probability of these enclosed walls on the tail of my distribution I showed previously, you'll have larger radii, which means larger masses, and will make it easier to form PPHs once they collapse. So once these walls enter the horizon, now Hubble cannot stop them from collapsing. And as I'll show you in a sec, is that these walls will then very quickly collapse, will shrink relativistically, and collapse near the speed of light, potentially forming a PVH. Okay.
Is it likely this wall will run into some string?
Yes, so there is another chance exactly during this scenario, you can run into another string.
There's one string for Hubble, right?
Yeah, exactly. And so I'll have a little slide on it. It's a subdominant effect, but basically you can imagine if I have a particle, a sphere of my enclosed wall, and I've got a bath, a medium of all these other strings surrounding it with some velocity that may impinge on it. And what's the chance of it hitting on it? You can show it some exponential probability of it colliding with it. And basically it reduces the number density of enclosed walls that don't hit a string.
Exponential because we don't have that many.
So what I mean is that so you can find the rate at which the strings will impinge on the wall. Right? And so the probability after a given time that the wall does not hit a string is e to the minus gamma t, right? Something like that. So most of these walls will hit a string, right? But it's going to be some fraction that gets suppressed compared to the exponential abundance to begin with. So it's smaller than that. I'll talk about it a little bit at the end, but it's something we have to take into account when we do. Okay, so what happens to these walls once they re-enter the horizon? So what you normally would do, or you would expect, is to be able to use this Nambu-Goto approximation, which is known as the thin wall limit. And what in the thin wall limit, this Nambu-Goto equation, is that you expect that the energy of my wall, my mass per area times my area at re-entry, is equal to my energy of my wall later. So it may have some smaller radius, but it has some Lorentz factor because it becomes more and more relativistic. And if you do that, what you'll find is that my Lorentz factor grows as my initial size of my wall at re-entry compared to my radius when it decreases. So as my radius decreases from the wall shrinking, my Lorentz factor can grow dramatically. And so this is what you expect. And if you do this, you would find that the wall can get hyper-relativistic and it can shrink to an infinitesimal point because it's infinitely thin. But in reality, you have to take into account the actual thickness of the wall. It has finite thickness. In this case, the finite thickness can prevent the axion wall from fully shrinking to an infinitesimal point. At the same time, the thickness can also give rise to axion emission, which is not included in this Nambu-Goto limit.
It's also not spherical.
It's not perfectly spherical, yes, but so this is what I'll show for nearly spherical walls or for walls that are of some typical shape, say a typical mean curvature radius R, right? That will shrink initially, and this will not be a bad approximation of the initial onset of the wall evolution, right? But then what happens is the thickness of the effect, the thickness becomes important, and asphericities also become important, right? So this was first pointed out actually by Widrow, that the thickness of the wall is something that's very important, and you can't just solve the Nambu-Goto equations when looking at the collapse of these spherical or nearly spherical walls. And so this is something what we do. And here I'm just giving an example first of a perfectly spherical wall, but I'll answer Leanne Tao's question about how this changes with aspherical walls. But it's nice to do first the spherical wall case to get intuition for what happens to the wall in more general geometries. So here I've got in blue on my top panel, I've got my axion field as a function of my radius from the given center of the wall. And these are in units of my thickness of my wall, which are of order the inverse axion mass. So again, I've got my wall, which interpolates between theta equals 0 and theta equals 2 pi. And I've got this change in my axion field, which tells me I have a lot of energy density localized at this point where my field changes spatially. And that's shown in orange on the bottom panel is the energy density of my axion field. So you can see you've got a wall is just a large concentration of energy density within a thickness of order delta here. Okay, so this is my starting configuration. As I just let the wall evolve with time, what happens is it wants to shrink and it will rush towards r equals 0. It will start shrinking towards the center. However, you'll notice a couple of things. First is that the thickness of the wall actually has decreased a little bit. And the reason is because as it's decreasing in size, it becomes more and more relativistic. So it gets Lorentz contracted, the thickness that is. And indeed, it does follow quite close the Nambu-Goto approximation for how the Lorentz factor changes as a function of radius, but only up to a certain point. You can see what's happening is as I shrink my wall, I start deviating from this nice kind of tangent function that interpolates between my normal wall, my initial wall. In fact, you can see what's happening is I'm developing a little horn. And the reason is because in the Laplacian of my equation of motion, that piece that goes as 2 over r ddr can actually become very big compared to my potential energy, and that totally breaks down the normal Nambu-Goto equation. So that piece actually becomes big. In fact, it becomes more like just solving a relativistic shell of light that's collapsing. So it becomes more like the wave equation than the sine-coordinate equation, which you try and solve. So what happens next is the wall totally deviates from the normal Nambu-Goto equation, and the field rushes towards the center, and you get huge amounts of energy density in a very small size, roughly of order a Lorentz contracted wall thickness here. You can't contract it indefinitely, of course, because of this thickness prevents the wall from fully contracting. Once it contracts, it hits itself violently and basically will emit tons of axion emission as a shell hits itself, and it partially goes through itself. It's partially transparent, but during this violent collision, it will emit many axions, and you can see these wiggles, which actually are emanating away radially, are axion waves that are lost from energy, are lost to energy as the wall hits itself. And it will shrink, it will expand again to a slightly smaller size, and it will keep contracting and expanding, losing and emitting axions with each bounce. So this is kind of the
Picking some axion mass.
In this case, this is just all in units of the radius of the wall, in units of the thickness of the axion, independent of the mass. So what you can show for this equation of motion here, that you can rewrite your units in units of the inverse axion mass of thickness, and that's the only thing that's physical is the radius of the wall to the thickness of the wall to the axion inverse axion mass. So it's independent of what actual value of your axion mass you define. So that's why it's in units of delta. So you can choose whatever MA you want. All right, but what we care about though is how much energy I can contract within a given volume, because that will tell me whether I can stuff enough energy within a Schwarzschild radius. So again, this is first for the perfectly spherical case. We'll discuss right afterwards a spherical case. But it's good to get some intuition what happens here first for spherical. And here on the y-axis, I show you the energy enclosed within a given radius as a function of that radius enclosed. So each contour here shows a different starting radius, r reentry, compared to the wall thickness at reentry. And as I go from blue to orange to green, etc., here, my initial size of my wall gets larger and larger and larger. So what's happening here? Well, the larger my initial wall is to begin with, the more I get Lorentz contracted as I shrink. And so my wall thickness decreases from this Lorentz contraction, and I can stuff more and more of it into a given smaller and smaller volume. And that allows me to enclose more energy within a given fraction as I go to larger and larger walls, okay? However, what you can see is that there's a sharp cutoff, relatively speaking, of order, a radius of order my wall thickness delta. So what that tells me is that it's actually fairly hard to contract my axion domain wall into a thickness of order the wall thickness, into a size of order the wall thickness delta, which is again the inverse axion mass. But the larger my wall is to begin with, the more I can shrink it, I can collapse it because of this extra Lorentz contraction factor. And indeed, that's what we find numerically, and analytically, you can understand that from this result, and that for very small radii, I can only contract a certain amount of volume. So my energy density within a very, very small radii below this break is roughly constant. And it tells you my energy enclosed goes as R cubed, which is indeed what we find numerically. And that this behavior, or how my energy enclosed increases with a given initial size of my wall from the Lorentz contraction, goes as my volume of my wall thickness, my Lorentz contracted wall thickness, and it agrees very beautifully as shown by the dash contours compared to the solid ones. So qualitatively, that's how to understand what is happening here for the perfectly spherical case. Now, as Leon Tao brought up, these walls are not perfectly spherical, right? We've been making the spherical cow approximation so far. But as I showed you previously, we can get statistics from these continuous random field simulations to estimate how spherical, or how aspherical, I should say, these typical walls are. And they do have some typical mild asphericities to begin with. Now, the question is like, how do we simulate these asphericities, and which ones should we care about? And I'll say that generally the largest scale asphericities on the walls are most important for two reasons. Is that one, excuse me, as I showed earlier on this kind of picture of scaling qualitatively, is that motion that is sub-horizon is free to move around, and it will typically intersect and emit axions or gravitons, and will damp away. So typically curvature that's much smaller than the horizon size gets damped from previous emission, previous motion. The second reason why these small scale asphericities are not as important as the larger scale asphericities, like the typical mean ellipticity of my wall, is that you can do actually mode analysis, as Widrow and others have done for the collapsing and closed walls. And what they find is that actually the small scale asphericities are damped compared to the large scale asphericities. So large scale asphericities can grow dramatically and really hinder your collapse of your wall into a very small volume. Now, I put this in with a caveat in mind because these analyses were done in a Nambu-Goto picture, which is totally breaks down anyway for very small radii from the finite thickness effects, which I discussed earlier. Nevertheless, we do find that these large scale asphericities can grow dramatically at the very end stage of collapse and can hinder somewhat the PBH formation. So to do this for purposes of computation, what we do is we simulate the full Euler-Lagrange equations of motion, not just for a perfectly spherical wall, but for a wall that has some given asphericity, some given semi-major and semi-minor axes, to see how these how this energy that I enclose with a given volume changes as a function of this asphericity factor. Okay, and so what we do find again is that asphericities, do hinder collapse, do hinder how much energy I can enclose within a given volume to some extent. They become most important for very small radii of collapse when my asphericities really grow dramatically. However, if you can form a PBH before those asphericities really grow, that is, my Schwarzschild radius is large enough that it becomes greater than when these asphericities really grow, then you can form a PBH more easily. So let's look at this a little bit more carefully. So as I said, these asphericities really grow dramatically closer to, for very small radii. So here I'm showing on the y-axis my fraction of energy enclosed within a given radius compared to the perfectly spherical wall of the same initial radius, but with no asphericity to begin with. The blue, orange, green, and purple and red contours show a wall, the same initial mean radius, but with some asphericity. That's some given semi-major axis that's 1.1, 1.2, 1.3, 1.4 times bigger than the normal test case. Okay, and what you see is this, is that for very large radii enclosed, much larger than the wall thickness, I still am able to collapse my wall into a given size. But as the wall gets closer and closer to its thickness, it really pancakes out, and it really prevents a large amount of energy within a given enclosed radius from occurring. And indeed, it becomes more severe. The suppression from asphericities become more and more severe as the wall starts off with a larger asphericity to begin with, right? So what you really want to form a PBH is you're gonna wanna form a PBH before this asphericity and suppression really kicks in at the final stages of collapse. So this does hurt PBH formation somewhat. But we can combine all of these results, like these asphericity parameters. We have statistical distributions for how these walls are typically, or how aspherical they are. Again, they typically have an asphericity of order 1.4 in one direction, say about 0.6 in the other direction, which is again the radius of the ratio of the semi-major to mean axis.
Is it computation done in the expand universe or?
Yeah, so two things. So one, we did both. Most of these simulations, like the one I showed here and the one I showed here, are done solving the Euler-Lagrange equations without Hubble, because the wall is assumed to be subhorizon by that time, and Hubble is small compared to the other terms in the parameters. But we also simulated how, in fact, the growth of the wall increases with Hubble to confirm that it does scale as the scale factor. And we also looked at how the asphericities changed with the expansion of the universe as well. And so typically the expansion does change the asphericities by a mild amount, a little bit. Most of the walls we consider are not going to be expanding for many orders of magnitude, because those are just too rare. You need a very large wall to begin with to expand for many orders of magnitude in time, right? Which are just very rare. So for walls that are slightly super horizon, which can expand a bit, the asphericities do change. Initial asphericities do change a little bit. They get damped actually a little bit by the time they re-enter the horizon, but it's a small, if I recall, like 10% effect or so. But these guys are simulated. Once they're sub-horizon, we neglect Hubble because it's small compared to the other terms, which makes the numerics much easier.
How this simulation where you start from some non-spherical configuration and it collapses? I just worried about the effect where this minor axis enter the horizon first.
Yeah.
That effect included.
Yeah. We tested that. And so what happens is like the minor axis can enter slightly before the major axis does, and you think it gets a little bit more pancake. And if I recall, it actually it doesn't. It's very small effect. That's a 10% thing. But we checked both because we were worried exactly about that. Because you could potentially imagine you can get a wall that's like, it starts off somewhat mildly aspherical and becomes super aspherical by the time it re-enters, but that doesn't happen actually.
I see.
Yeah. Okay, good. So I have how much time do I have left? 5-10 minutes or so? 5 minutes? Okay, cool. So let me just wrap up real quickly. At the kind of combining all these results, the number density of enclosed walls, which we have as a function of their size, and given an initial wall size, how much we can compress it within a given volume. We want to combine these results to figure out what the PBH abundance is for QC axions or axion-like particles. And as Lantau asked earlier about what mass I was taking, what actually is kind of beautiful about most of these results is that it doesn't matter the mass. But actually, the only physical thing that enters is the radius of the wall compared to its thickness, and that becomes the parameter of interest. And you can mimic that, or you can match that to various axion or alpha-like particles. So what I'll say just very briefly is that there are kind of three parameters which affect the abundance of, or the ability to form a PBH. And one is this axion decay constant Fa. As I said earlier, the larger Fa increases my wall tension, which means my mass of my wall is larger, which increases my Schwarzschild radius, makes it easier to form a black hole. Smaller delta means I can compress my wall even more. And then finally, there's this factor alpha, which tells me my initial wall size, how super horizon it is. The larger my initial wall size, the more mass I'm going to have by the time it re-enters the horizon, the easier it will be to form a PBH. Okay, so from our simulations, what we computed was this fraction F, which was the energy enclosed with the given radius compared to the total energy of my wall system, which we know what that is. It's roughly the area of the wall times its wall tension at re-entry. And what we want to do is to find whether we can form a PBH, is we demand that the radius, which encloses the given energy, has to be less than the Schwarzschild radius of that given energy. So my Schwarzschild radius, 2GE, times the energy within this given R enclosed, we demand that this R enclosed be less than this value, which again, we can use from this equation, we can write in terms of my initial energy of my wall, which we know, as well as the numeric factor F, which is how much fraction of my energy, my total energy that I enclose with a given radius. From this equation, you can actually solve for a minimum wall size to thickness at reentry that satisfies this, that makes it such that I can compress enough energy within a given size to compress enough energy to be within a given Schwarzschild radius. And I'll show you very briefly kind of what this looks like as a function of FA. So the y-axis shows the minimum reentry radius compared to the thickness to form a PBH as a function of FA for different values of my asphericity parameter. So for the blue, I've got epsilon of 1, it's exactly spherical, okay? And what you find is that, as expected, the more spherical the wall is, the less amount of, the smaller the minimum radius of your wall needs to be able to compress enough energy within a given Schwarzschild radius. But more aspherical walls, you have to have larger and larger initial wall sizes to compensate the loss from suppression of asphericities with the extra energy you get from a bigger wall, right? And generally, what you see is, again, the larger FA, the easier it is the smaller this minimum R reentry will be to form a PBH. And what we can do is we can compare this, or what we do is we relate this guy. This is cosmology independent to cosmology by relating this radius at reentry to the thickness at reentry to cosmological parameters and the number densities of enclosed walls that we discussed earlier. So this radius at reentry compared to the thickness at reentry, you can write in terms of my initial wall property, which is related to alpha, that is how super horizon it is, which is again is related to those continuous random field simulations that we did previously. My radius at reentry compared to my radius at formation, which is related to how much time the wall spends outside the horizon, as well as any thickness effects that the axion mass may turn on and may grow, which actually helps you slightly for compressing this guy into a given volume. So for lack of time, I won't go into this, but maybe Lian, we can talk afterwards. But this is exactly, I think, what you were asking about colliding with other defects. And yes, it does hurt you to some extent. It depends on how big you are. Because the bigger you are, the more you'll expand, the greater your chance of probability of colliding with another defect, and that can hurt you. We combine that with we tack on that probability of colliding onto the number density of walls that actually form PBHs. So that is taken into account. So this I'll wrap up with this slide and then one more for the money plots, showing you the fraction of PBHs as a function of FA. So here is for the QCD axion. And it shows that for very large FA, closer to 10 to the 16 JeV is where you can actually get a more appreciable amount of PBHs. So ideally, in principle, you could take FA to be much larger than 10 to 16 JeV, which you can't, which is difficult to do. You would be able to get a much larger fraction of PBHs. There's one caveat for the axion, the QCD axion, which is a little bit annoying, is that for the QCD axion, because the walls form near the QCD phase transition, I can't actually have FA be so large because I actually overproduce the axion dark matter from the normal misalignment mechanism. And normally for FA greater than 10 to the 11 GeV or so, you have to dilute that abundance of axions, QCD axions, to get the right dark matter abundance. But you can only dilute them so much because once you dilute them, you can't have a reheat temperature, you can't dilute them below the BBN scale. And because QCD and BBN are not that far off, you can only take roughly an FA for a consistent cosmology around a little bit greater than a few times 10 to the 15 GeV without diluting too much, without being able to dilute enough dark matter. So for the QCD axion, it's harder to get FPBHs much greater than 10 to the minus 10, unfortunately. But for normal axion-like particles, which don't have necessarily this overproduction problem, and you can have the walls form at different points in time, you basically have the exact same fraction of PBHs as a function of FA, but without the hindrance of consistent cosmologies for lower FA or for larger FA. So I'll just wrap up for time and just say that for axions, so these axion cosmologies, like I said, they can generate these enclosed walls, which can collapse and potentially generate PBHs, with the abundance as being as largest for larger FA. So for the QCD axion, because of this BBN bound, it's very hard to get FA much greater than a few times 10 to the FA, few times 10 to the 15 GeV, which makes it a little bit difficult to get fractions of PBH within next generation observatories, lensing observatories like Roman. However, you can apply, this formalism applies almost identically to ALPS without necessarily this bound of consistent BVN. So you can have much larger FA for ALP models and get much larger FPBHs that potentially could be observable. And what I was telling KSK earlier is that, I'm actually most excited to apply this, not to QCD axion models, but to other models, so for example, walls and strings and grain unified theories, where you can generally get much smaller mass PBHs because the horizon when these walls form can be much earlier in time, where the masses of the PBHs, which are set by roughly the horizon size and the wall tension, can be such that their masses may be in this mass range between 10 to the minus 17 and 10 to the minus 11 solar masses, or potentially all of the dark matter could be PBHs. So there are some differences between that and this model, but I'm very excited about applying some of this formalism to that. So thank you.
Thank you, David. A very interesting talk. Questions? I have one question.
Sure.
So here, when you say the PBS can be all of dark matter, but there are a majority of the strings and or the walls are actually not enclosed, but they will emit axions, right? What about would they be overproduced then in this scenario where you're trying to make PBH
in this
all of
case.
dark matter?
Yeah. So in this case, I'm talking about not necessarily axions. So there would be models where you have some grain unified theory where you get strings, and then those strings that can become later attached to walls, and the whole network will decay. So you don't have axions per se in those models. So
Oh, but there are still like kind of walls that are enclosed by strings. They're not
Yes.
closed,
but
but
yes,
they will
These
like
are just-
gravitational waves or
those will decay and
Discrete symmetry like C2.
yeah, for example, right? So you can get you're talking about walls attached to strings and
Yeah.
so you get those, and those are the majority of the
Yeah.
signal, of the defects that form. At minimum roughly 1,000 times for every enclosed wall, you get 1,000 wall bounded strings roughly. But those guys will decay and emit gravitational waves, and most of their energy gets diluted into radiation.
Okay.
But these guys, if they can form PBHs, they can, a very small amount, they redshift much slower than dark matter, than radiation, excuse me. And so that's how they can win out. Even though they start off with some much subdominant contribution, they can eventually win out.
I have to imagine the gut phase transition happens at lower temperature than gut scale.
Yeah, so the question is,
Otherwise, we don't reheat that.
yeah, so you need the reheat temperature rate. So you need strings here, and you need the reheat temperature after inflation to be large enough that you produce strings, or at least you have strings that re-enter the horizon by the time the walls form, or you care about
Some
that.
other way, yeah.
Exactly. So you're getting close to bounds on H inflation, right? From having too large, but in principle, I think you may be able to, you can do this, right? That's something I'm working on a little bit more now. So yeah.
So for generic domain, we will still need a large wave for the symmetry breaking field to have a large PBH abundance, like close to gut scale.
Yeah.
Like 10 to 10 GB or so doesn't work, I guess.
Right. So the other difference between the gut case and the normal axion mass case is that for axion walls, sigma, as I said, is MAFA squared.
Yeah.
Whereas for this is axion, and for guts, as KSK is pointing out, the typical sigma is of order the gut scale cubed, right? And so
Actually, mass time got square, it should be.
mass, the mass of the heavy field associated with it.
Yeah.
Cubed, right? So there's coupling constants out front here, right? So what do you mean? But parametrically, just squiggle, right? I guess I expect of order B gut.
If we just identify with mass of the direction times wave square, it is okay that this mass is small, but wave is large, like gut scale. In that case, you can roughly use your just ALP scenario.
Oh, like this tension, sorry.
Yeah, you say that this is independent of mass.
Yeah.
or the width. So this means that if the sigma gat is mass times v square, we should just it's okay to take mass to be small and the v to be large.
Yeah, so right, so
If
you're
you
saying.
like a really small quantum.
Yeah, so you're saying, imagine your field is like something like this, you can take lambda to be very,
Yeah,
very small.
let's take lambda to be small. So then it is v that basically determine the fraction of pH that abundance.
Right, so what enters, yeah, so I haven't considered the case where lambda is much smaller than V. But yeah, you get, you have to be careful with the physics there, but as you say, what enters into these PBH formation bounds are the ratio of the wall to the thickness typically. So that's what actually enters, and so, I mean, I have to be careful with this guy, and I mean, Casey, maybe we can talk a little bit more after, I don't fully understand what you're saying about taking lambda to be very light, and then that.
I just thought in your arc plot, you said it's independent from the plot is independent from the arc mass.
Yeah.
So you're just saying the lambda actually cancels in the.
Yeah, I thought that's what you say.
The conic actually cancels.
Oh,
Because R is the correlation length of this guy, right? So.
yeah, well, what I mean is like, I mean, the equation of motion, right, for the axion, right, it's something like ma squared fa squared times this chunk, right? And so you can rewrite everything in terms, just quantitatively to see this. You can rewrite everything in terms of units of I guess this is, yeah, ma squared. Right, I'm sorry, ma squared. You can rewrite this in terms of 1/ma, and so the only physical units become the mass. So the equation of motion for the guts will be maybe a little bit different. And so that could be something that will change it a little bit. Right.
We can discuss afterward.
Okay.
Yeah.
Cool.
Any other questions? If not, let's thank David again.
Sure.